Yeah, Dr. Hemant, can you hear us? Can you hear me?
Yes, very much.
Yes. Okay. Okay. So, welcome you, sir, to our FDP on AI in medical imaging and diagnostics. So, thank you for joining us today, and it's our pleasure to introduce you in front of our participants. So, let me just introduce you. Dr. Hemant is working as a staff scientist at GE Healthcare Bangalore, India, with broad research interest in inverse problems and physics-inspired deep learning. He received his PhD in computer science in the year 2016 from IIIT Delhi. As a postdoctoral research scholar in the computational biomedical imaging group at the University of Iowa, USA, he developed novel algorithms for accelerated parallel and diffusion MRI. He's serving as a guest associate editor for IEEE transactions in medical imaging, one of the best transactions in the field of medical imaging. He had received a Distinguished Reviewer Gold Level Award from IEEE TMI. His collaborative research on parallel imaging got the Best Machine Learning Paper Award at ISBI 2019, which is one of the renowned biomedical imaging symposium or conference, you can say. He was nominated for the Emerging Investigator Award at the Imaging Elevated 2020 Symposium at the University of Utah, USA. So with this introduction, now I request Dr. Hemant to please start the session. Right. So I'm sorry actually for late joining. I have joined actually 5 minutes late. I'm late. So please, over to you. Please start,
Sure.
please.
Thank you, Deepak. Thank you so much for the kind introduction, and thank you for this opportunity to present our research work here in this FDP program. Yeah, sure. I'll just okay. I
Yeah,
hope
it's
my
visible.
screen is visible.
Yes, yes, yes. It's
Uh,
visible. Kindly make it full screen and start the session.
yes, please. Okay, so yeah, I am in the full screen mode. If you guys have any questions during the session, please feel free to speak up or just write in the chat. And I hope some of the organizer will be able to help me with the questions. Like if there is a question, just notify me. Okay, so yeah, with that, so basically today we are going to talk about model-based deep learning and with this application into kernel synthesis. So there are two things. One is the model-based deep learning, which is the AI part. That is what we are going to discuss today. And second is the CT kernel synthesis. CT is computed tomography. So one of the application area, one like a problem statement. So you take a problem statement of CT kernel synthesis. We will go through what it does it mean by kernel synthesis. And we will also go through what does it mean by model base and the deep learning. Okay, so we'll go through everything. So two aspects are there. One is the physics aspect. The problem statement is in the medical imaging problem. And the algorithm wise, it is a model based deep learning architecture. Basically, not single architecture, but a series of architecture which are also called unrolling based architectures. Okay. So what? So this is just a disclaimer that this work is not available right now in any of the products and may not be available. Okay. This is just a purely a research project that we have been doing here. And I have developed this model in the past. So I'm presenting that one, not necessarily available in the commercially. So what we are going to discuss, okay, I will describe what is a CT kernel synthesis problem statement. So at least everybody should be able to understand what is the problem statement that we have been working here. And then why it is an important problem, in particular in the image domain. And then how do we formulate it as an inverse problem? So I typically work on, as Deepak mentioned, on the inverse problems. Okay, so how do we formulate it as an inverse problem? And what are the various solutions? So at least two solutions we are talking here. One is a direct solution, one is an analytical solution. What does it mean by that? We will see. Okay, then we will talk one particular architecture in a supervised setting, which is called a model-based deep learning architecture. Then, if the time permits, we will see the self-supervised architecture, which is a Newman architecture, which is another architecture based on model-based deep learning only, but inspired by the Newman series. We will see the details, okay? So basically, what you are going to learn is about two model-based deep learning architectures, a problem statement, and then finally we will conclude with some experimental results. Okay, so this is the overall context of the next 1 hour. So CT images are typically reconstructed with a specific kernel. So when we say kernel, kernel is essentially meaning exactly same as like a filter. So we have like various low pass filters. So just assume whenever I say kernel, it means a filter. and most probably it is a filter in the low pass filter. Okay, so this is the shape of the different filters for your example. Okay, so here I'm showing four kinds of filters. These four kinds of filters are four different filters. They have a name specifically: standard, lung, detail, and bone. What does these filters? They have a different frequency response on the y-axis, you can see, and they have a different bandwidth here. So for example, this red one is dying around here, whereas this blue one is dying around here. So what does it mean? It means the red one is having a lower bandwidth than the blue one. So blue one has higher bandwidth, which means it has more details in the data. What does it mean? We will just see. Okay. So these are the different kinds of low pass filter in the terms of signal processing. In terms of CT, what happens whenever you are reconstructing a CT image? So for example, a patient goes into the scanner. What do we get out of it? We get a sinogram data. What is a sinogram data? Sinogram data is a raw data that you get out of the scanner. Okay. Once you have the raw data available, you do the reconstruction. During the reconstruction process, you use one of the kernel based on the application at hand. And that is where these kernels are used to reconstruct the images. So when you reconstruct an image with a specific kernel, which kernel again I am telling you is just a filter. When you reconstruct an image with a specific kernel, it is looking like this. For example, if you take these four kernels I showed you, right? Red, green, blue, and the yellow one. Okay, so they have a different impact on the different images. So the same image, if I'm showing you standard and the lung kernel, they look very different. Okay, so this is a very smooth image as compared to this one. This is a sharp image. So this standard and the similarly, this one below one, detail and the bone, these are the kernels with different bandwidths. Okay, and they are looking what is different here. Here, if you see, for example, here in this region, what is the difference? Difference is in the sharpness of the image. So here you have more details, like very easily visible as compared to here. So it really depends on the application that you have at hand. So the choice of the kernel, how do you choose a kernel to do the image reconstruction? Okay, so it really depends on the downward task that you are doing. So what you are going to do with an image? If you are given an image like this, which is reconstructed using a smooth kernel, so it has applications doctors decide, which kernel you should use to reconstruct the image. So if doctor want to see some of the soft tissue areas where you want less noise, whenever you want to see less noise, that is typically in the bone area here, then you use a smooth kernel. But when you want to see, for example, inside the lung, every single detail inside the lung parenchyma, okay, so these are way more sharper than the left image. So the same slice, which means you have the sinogram data available to you, then you reconstruct the left image with the smooth kernel, right image with a sharp kernel. What is the difference? When you should use which one? That depends on the application at hand that doctor describes based on what the doctor has an interest in looking at. Okay, so basically you may need the image of any kernel. That is the idea here. So if you reconstruct the image with one kernel, can you make the second image from the first image? That is the question that we have. So what is the kernel synthesis? When somebody says kernel synthesis, it essentially refers to converting one kernel image to another kernel image. For example, you are given this kernel image. Okay, so this is the image of inner ear. So the ear is there, right? So this is the right inner ear image. So if you want to convert this image into a bone kernel image, which is a sharp image, what action you will take if you do not have a sinogram data available to you? So this is the problem statement that we are looking at today in this talk. So in the absence of sinogram data, which means you do not have the raw data available to you. So you had the patient coming to the scanner, got the sinogram data, and you reconstructed, for example, with a detailed kernel. But later on, the doctor came and said, no, doctor want to look in the bone kernel image. You can see inside this image, right? So much more details are available here. So you can see inside here other soft tissue texture is very nice, as well as inside the bone. There are a lot of details available here with respect to, if you just compare with respect to the left image. Okay. But the problem is you only constructed your data with this one. And later on, maybe after a few days, you need the image with this one. or on the software itself, when you are visualizing the images on the software and immediately you want to visualize some pathology into this one, then how can you do that? So that is the goal. Okay, so if you already have the sinogram data available to you, then you have no problem. Then you can simply reconstruct the raw data, but it is very expensive to reconstruct. In the sense, it is not a simple reconstruction. Reconstruction from the sinogram data to the image domain data in reality has a lot of steps involved. It's not a single inverse Fourier transform or something like in MR that we do. It's not like that. Okay, so it is much more involved process in reality. So you want to convert from left to the right. That is the goal. Or you want to convert in from the this kind of image, from the standard to the bone, standard to the lung, or from the this kind of detail to the bone kernel. Basically, one filter to another filter. So what is the natural step that we can do? We can always do a direct kernel conversion. So that is the first technique that we are going to do. How you can simply convert. Given you are given only the a kernel, which is a detailed kernel, and then you want to construct the image. So this is your input image which is given to you. And of course, when you are given the image, you also know what is the MTF. MTF refers to the absolute value of the Fourier transform of your PSF. In this case, the kernel is specific kernel. So if you are given a specific kernel and the corresponding MTF, how you can reconstruct to a different kernel. For example, in this case, the lung kernel, right? So you want to make left image as sharp as this. So the simplest process is the forward process, which means you construct your, this is a linear operation. You can see it is just a matrix vector multiplication. So you are given the left image as an input. If you know what is the A operator, then you can just multiply with this and you can get your output, the lung kernel, which is the right image. Okay. So, and what, how do you reconstruct this, the construct, the A operator? What is this A operator? In this case, this is a very similar to your, what you say, in deblurring problems or deconvolution problems or super resolution problems. What you do, you take a Fourier transform of your image, then apply the filter into the, this is a ratio of the filters. So whatever is your target kernel, this, in this case is the this kernel, the kernel which is a lung kernel. Okay, so a ratio of the 2D MTFs of the these two kernels, that makes your this operation, which is essentially nothing but the Fourier domain filtering. And then you take inverse Fourier transform to get back the image. Okay, so yeah, I'm just will take a pause here. If anybody has any doubt in the direct kernel conversion process, just let me know. Okay, so I hope this is simple matrix vector multiplication. If anybody has any doubt, to let me know. If problem statement note ke liya, any doubt.
Yeah, they can only write their queries in the
Okay.
chat box. So
Okay. Yeah, guys, please go ahead and write down. And if there is a question, yeah, somebody from the organization team will help me with the question. Okay, so please go ahead and write your question. Whenever it is there, we can discuss. Sure. So we'll go ahead. And so what is the problem with this method? Okay, this is a very simple method. Whatever is the problem? Problem is a linear filter will enhance everything. It will enhance your noise. It will enhance your artifacts. So you can see all the noise from the left image has enhanced significantly here. So what is the noise here actually? So if you look inside here, this region, so everything here is this thing also gets enhanced. Okay, so this is noise. So it has a lot of noise that got elevated because it is a simple linear filtering. So if you do that, then you enhance the noise very much. So what you want? So the goal is do the kernel conversion, but control your noise and control the artifacts. That is the goal here. Okay, so that is why simple forward model cannot work. If you do a simple direct kernel conversion, it does the job, but is not very good. So this is not what is desired output. You do not want the artifacts to get enhanced. Here the artifacts, all the streak artifacts have got enhanced significantly. Okay, we don't want that. So can we do better? That is the question. So of course linear filter works, but can we do better? So yes, we can do better. And how? The obvious answer is we can use a deep learning kind of thing. But for that, firstly, we need to form it as a more just a forward rather than a forward model. We use an inverse problem method. How do we represent that problem? So we can represent the kernel synthesis as a linear inverse problem. How do we do that? Just the same way. So you have the input kernel image which is given to you, and then you have the target. I mean, you do not know what is the target image. You want this X. And then A operator is what you know. What is the A operator? A operator is the ratio of input to the target kernel. Okay. A is the ratio of input to the target kernel. So you have the 2D MTF of the input kernel, 2D MTF of the target, and you simply take the ratio. And then in the frequency domain, you are applying it here. You take the Fourier transform of your data, apply the just element wise multiplication, then apply the inverse Fourier transform, you will get back the image. Okay. Once you know Y and A, then the simplest process is X is equal to A inverse Y. That will give you the output. Okay. But that is a simple linear filtering that will not do the job. Okay. Because there is no unique solution to this problem. Therefore, it is an ill-posed inverse problem. Because if you reduce the noise little bit, okay, so for example, very little from a single pixel, if you reduce the noise, this is better than your input image. Okay. But that doesn't mean it is the best image. Okay. So to get the best image, you really want to reduce the artifact throughout, which means you have multiple solutions available. There is no unique solution to this problem. Therefore, you want to do something called a regularization that helps you. Okay, so whenever you have a ill-posed inverse problem, you typically almost always solve it using a regularization technique. Okay, what does that mean? That means this. If you have a forward model like this, then you directly, rather than directly solving x hat is equal to a inverse y, rather than doing this, you do this. What you are saying, you are minimizing the error between y and ax. That is like you are minimizing the noise, or that is also called data consistency term, or that is also called ensuring the physics. What is the form of A? That really defines it. Okay. Plus you put some regularization or the prior information. So this is your prior. You put some prior constraint on your in on your solution that you want. So in case of images, we already know there are several kinds of prior which are very popular. So not only for the kernel synthesis, but for any general linear inverse problem, like for example, denoising problem, or MR super resolution, MR image reconstruction problem, or deblurring, deconvolution, many different kind of problems you can formulate into this form. Then all of them follows the common path. So the most common and widely used and the simplest way to use is the Tikhonov regularization. Okay, so what does it say? It says the regularization is Tikhonov, which just imposes overall smoothness. So we know L2 norm square is like energy minimization. So which means energy is less, which means if there is a noise, then only you have very high energy into the signal. So if you reduce, so this basically this is promoting a smooth solution which has less noise. Okay. Total variation, we know we can always treat our images as a piecewise smooth images. Okay. So and then we can use total variation as a regularizer. There are many other kinds of regularizer. Another popular one is a L1 regularization. Okay, so you put some kind of sparsity constraint on your reconstruction. But the one which we are interested in this talk is the CNN based or the learning based regularizer. So what does this regularization is? I told regularization is a prior information. Can you really learn the prior information from the existing data? Okay, and then use it as a regularizer into this problem formulation. That is the kind of problem that we want to solve today. Okay, so but let us first see how do we, if we simply use a simple regularizer, what happens? Okay, and then we will move to the fourth one and we will skip these two. Okay, so this is, by the way, true for all kinds of problem, as I mentioned, not just, so this is true for any kind of linear inverse problem, not just your in imaging, not just this particular kernel synthesis problem. Okay, so if you have this basic problem, okay, this is a Tikhonov regularized cost function. So regularization is a Tikhonov norm and lambda is a just a parameter that says how much weightage you want to give to this regularization term. So in case of kernel synthesis, okay, we can solve this analytically. Okay, so that is what do we mean by analytical solution now? If because both are L2 norms, we can simply take the derivative and put it equal to 0. So just like a regular, minimization problem. So this is a minimization problem, which is a differentiable function here. So the derivative you take, put the derivative equal to 0, what you get is a solution, and that solution is what is your minima of this problem. So just like your 11th and 12th you used to do. So you take the derivative, put it equal to 0, what you get is a normal equation. Now in our case, we know what is the A operator. A operator is this operator. What is A transpose? That's just the transpose of this. Now if you simplify this operation, so here you know like F transpose F is a identity. So this is gone. So you only have a solution here. So basically what we are saying here, these normal equations, which you can solve using any linear algebra. But it requires another inverse of this matrix. This is a very interesting matrix. It is always positive semi-definite. Okay, if lambda is greater than, yeah, this has a positive definite matrix. Okay, so there are lot of methods that exist in literature to solve this, but that is all iterative, which is more expensive. Can we solve it analytically? Yes, if we know the form of A operator. What is the form of A operator? Depending on that, we can further simplify. In our case, the A operator is having simple filter, the Fourier transform of the filter. So we are trying to solve it further. Can we further simplify it? So it turns out we can. So now from here to here we go. Okay, you see A transpose A I replaced with this. Okay, and lambda is as it is. Then what you do, you take the Fourier transform on both sides. And then you can see you can further simplify it. Just FF transpose goes identity, and this FX you takes common out. So you can get the solution like this. So this is a diagonal matrix, and inverting the diagonal matrix is very easy. Okay, just 1 by that is the diagonal. So the solution is very simple in this case, and you get an analytical solution. If you have a problem statement with the just Tikhonov regularization, and you have your A operator, which is having a specific form. In this case, A operator was just the taking the Fourier transform of your data, applying the filter, and then taking the inverse Fourier transform. This is the ratio of the MTFs. Okay, and we know what is our target kernel. Therefore, we can calculate the ratio. So if any doubt, please do write in the chat and let me know. Okay. So this is the analytical solution. Just remember, we discussed the direct solution, which is using just the forward model. Now analytical solution, which is supposed to be slightly better. Okay, but this says simple regularization. Can we do better? That is the question. Okay, so a neural network can always do better than a simple regularizer. Okay, I mean not always, but there will be a strong statement, but depending on how we are using it. A direct neural network training can be used, training using a supervised network can improve the result. Okay. So if you have to really train a neural network, how can you do that? Okay. So this is the input data set. Suppose you take a lot of smooth images. You also have a pair of lot of ground truth sharp images available to you. If these are available, it is not very easy to always have access to the large amount of the data, which is like in the medical imaging, exact same pairs. Okay. If you well design your product, because you cannot scan the same patient again and again, like CT, we are talking CT, which is having X-rays and all. So you don't have that luxury of scanning again, but you can reconstruct the data and then design your experiment. So in this case, you can reconstruct with the two kernel, get the data. Okay, and then you can learn a convolutional neural network, any neural network, for example, UNet, ResNet, anything. And theta we know are the parameter. Then what you do, you simplify this like this. I mean, you simply minimize the loss function. So you have an input image y goes to the network f theta. What you get is a prediction, network prediction, and then you compare it with the original image. So input image is yi here, target is xi, and you minimize the loss between them after getting through the. This is a standard deep learning method. Okay. What is the problem here? Problem here is you didn't utilize any of the physics information. So what do we mean by the physics information? So whenever you have the data available, you also have the corresponding MTF available to you. Okay. So, but not utilizing is not a problem. It only means can we do better if we utilize the physics information available to us. Okay. So, and another thing is it requires really very large amount of the data if you do not utilize the physics information available to you. Okay. So depending on the case to case, you have to wisely choose which network. Okay. So if you have very less data, unrolled networks are really helpful because they can train very well if you have a scarcity of the data. So if you have physics information, so what is the physics information? So this is the A operator that we are talking here. So how do you utilize this A operator in this training procedure? Okay, so definitely that is an extra information in the form of the MTFs. So how does that help? That is the question. Okay, so these are the two MTFs of the input and the target, which is just essentially the filters that are available to us. If we want to utilize that information, how can we utilize that? Okay, so so I just wanted to give you one example of if you utilize this information, or if you do not utilize, what does it mean? Okay, so the forward model has a lot of impact if you use that physics information. For example, I'm just going to show you some of the data that we have. So there is something called DFOV. DFOV stands for display field of view. DFOV stands for display field of view. Okay, so display field of view is like, for example, if you have a patient, no, here I'm just making here. So if you are doing a head scan, okay, so this much is your field of view. For example, typically in the inner ear case, you have like 150 mm. Okay, if you are doing full chest, okay, it is like 50 centimeter, which is like a 500 millimeter. I mean, just giving you an example. Okay, so this entire region is what you are. So for example, a cardiac scan is small, like half of that, which is like a 25 centimeter is the field of view. Divide by the number of pixels, that gives you the resolution. Okay, so if you have a different field of view and you already know at which field of view you acquired the data, that has a lot of impact. So what I'm showing you right now is the water phantom data, which is a different field of view. So field of view is one information that goes into the modulation transfer function. Okay, and that is your A operator that we formulate. Okay, so how does that matter is what we are seeing. So you see, if you have a DFOV 5, 10, 15 or 20, this is the same water phantom data. We are looking at different field of view, and you can see the resolution changes a lot, which means physics really has a lot of impact. And if you already know this information, how can you utilize it? This is good to utilize if you already know. So this is the forward model got changed from one image to the another. Okay, so 5 centimeters is very small. So you have a, like a very low resolution here. But if you go higher, you have a very speckle. So this is a water phantom is used like a noise. It is very much different from your Gaussian noise or Poisson noise. Okay, so in CT the noise is like dependent on the kernel also. So low resolution kernels give you very low resolution, and a high resolution kernel, which also depends on the DFOV value, will give you a very fine speckle. Okay, so that really matters. So basically so what I'm showing you here is a one example data set. But this is true for the general scans also. If you do the inner ear scan or the cardiac scan, or any scan you do at different DFOV and you already know the DFOV information, then you can utilize that information and get the better reconstruction. That is the goal here, right? So if anybody has any doubt, just to please write in your chat. Okay. So we'll continue. So now, how can we achieve DFOV independence using the model-based deep learning? Okay, so not really DFOV independence. We want to utilize the A operator. In this case, A operator gives us DFOV independence. Okay, so this is the same A operator, or like here I have written H by. Okay, so H is representing same as A. Okay, so how can we utilize that? Okay, so we know this solution. Okay, this is called direct solution or analytical solution. But the problem formulation is now this, it changes with model-based deep learning. When we say model-based, what is the model? Model refers to the forward model, okay, which is y is equal to hx, or in this case ax, okay. Then this first term is your model constraint. So this first term is called model constraint. So when somebody says model-based deep learning, it means they are using deep neural network only in the regularizer. So you are using some kind of CNN transformer or anything into the regularization term. But the first term is your data consistency term, which is also called model constraint or the physics constraint. Okay. And then this kind of problem statement, when you try to solve it, definitely you will solve it using some kind of iterative algorithm. Okay, so by the way, so here what is DW? DW is a CNN. What we are saying here, just try to understand what we are saying here. Okay, that is the most important part of this talk. So what we are saying here is the solution that we do not know. Okay, what we know here, Y we know, A we know. Okay, we are interested in X. Okay, so what we are saying, our solution, whatever we get, should be data consistent. That is the part one. And that solution, when you pass it through a neural network, it will give you some output. So network will predict something. Okay, suppose X hat. Now, whatever solution you get, X hat and X, that norm should also be minimum. So you are minimizing, which means distance between the data consistency and the CNN should be very small. And this is one way to put a regularization using a neural network. Okay. So what you are saying, the solution that you get from the data consistency step, which is X, that X, when you pass through the neural network, should be very similar. So the noise you are minimizing here, or the distance between the actual solution and the network prediction, you are minimizing. Okay. Ideally, you want what? You want X is equal to DWX. Okay. That is what you want. If that is not possible, next best thing is you just minimize the norm between them. That is the next best thing. Okay. So this is the constraint we are putting here. Okay. So this is the way you are putting the constraint. So this is different from a Tikhonov regularization, but very similar. So Tikhonov regularization was just this. I'm writing here on the top right. Okay. But what you are saying, X minus some Z. And what is Z? Z is a CNN output. So this is a different regularizer. This is a different regularizer. If you have a simple regularizer, you have a direct solution. But here you do not have a direct solution. How do you solve this kind of problem? A solution to this problem leads to something called a unroll architecture. Okay, and that is very well studied for last 10 years. Okay, so a lot of people have developed and they have seen very successful application, especially when it comes to medical imaging. Okay, so let's continue. Yeah. So there are multiple ways to account for the data consistency. Okay. So I told you, right? Just assume Z is equal to DWX. Then you have this kind of problem. Okay. So you just put here Z. Then you got this. Okay. This is the same problem. You take a derivative. Okay. Both are L2 norms. L2 norm is square. L2 norm is square. Whenever you have like this, you can always take the derivative. Okay. And when you take the derivative, you get this term. Then what you can do, you can utilize a gradient descent algorithm. What is the gradient descent? Next best solution is X minus alpha times the gradient. Okay. So now you put it here. So that thing, the solution update, you got it, right? Delta, this, you put it from here. So you just put it here, simplify it, you get Xi. So this is your gradient descent based update step. That leads to the solution to this problem. Okay, so here this is clear, right? This is just you are passing through a neural network. But this is the problem you have to solve. How do you solve it? In analytical solution, you have no problem. But in case of MRI, for example, if you have a multi-channel MRI or diffusion MRI, okay, so there A is not simply invertible. You always have to resort to some kind of algorithm. One way is gradient descent, another is a conjugate gradient. Okay, this is more elegant. What do you do here? You simply put delta is equal to 0 and you solve for this problem. So this you can solve using CG. In CG, this is your A operator and this is your right hand side, and you pass it through CG, maybe like 5 iterations of CG, and you get a solution. So that is what is the solution to your data consistency step. Okay, so yeah, again, I'm telling if something is unclear, do ask the questions. Okay. So together with this denoising step and a CG-based data consistency step, we can derive a neural network architecture. First is a neural network. Here, this neural network can be any neural network. For example, ResNet, any CNN or any kind of architecture. Okay, ResNet, UNet, anything. Then you have a data consistency step. Together, they make one iteration of. So this is the problem that we are interested in solving. Okay, this is on the top. This is the problem we are interested. A solution using alternating minimization is a two-step solution. Step 1, denoising. Step 2, data consistency. So together we route them into the blocks. Okay, these are the two blocks. And that gives you solution iteration 1. But you unroll it, for example, k iterations. Okay, and then finally you get a solution xk. Now on xk, you will put, if you are doing a supervised learning, xk minus ground truth. and then you minimize your mean square error, MA, any kind of loss function. So that will be your, this is your full network architecture. And then each of them, DWs, are your neural network. So neural networks, so they can be different neural network. You can be as innovative as you like. So in our cases, we simply use the same neural network, repeated the weights as many times. So we share the weight, but it is not necessary. You can have the different weights. Okay, so slight differences are there, but more or less you can use any architecture as well as many times different architectures, or repeat the same architecture in our case. Finally, you minimize. So this whole thing is called a unrolled architecture because you unroll the iterations of a optimization problem, solution to an optimization problem. Okay. So this kind of architecture gives you very good results. Okay, so here I'm just showing the comparison. In interest of time, we'll go on to some of the results. Okay, so now I'm showing you some of the results at DFOV 5 centimeter. Okay, so this is the actual real data experiment. So here you're seeing some of the results. This is your input image. Okay, this is your smooth image. This is your target image, which is your given image. Okay, so we had access to the this is a sharp image. You can see this is these two images. If you focus, you can see they're the same detail. It is just that left one is the smooth and rightmost is the sharp. If you utilize a simple unit, okay, this is what you get. Lot of artifacts you can see inside. If you utilize a like model-based deep learning kind of architecture, then you get much better results. Okay, so this is what we had worked on. And so now you're showing results at 5 centimeter. If so, you can appreciate the results, right? These are significantly better than a direct learning, because in direct learning, your network is doing a lot of work. The network is really learning the equivalent of inverse. That is very difficult task. Whereas in here, network is only learning as a regularizer, or denoising step, which is much more easier. That is the like intuition why this thing works better than this thing. Okay, left one. So second is you can see a lot of artifacts. Third one is better. Same is another example I'm showing, but this time at a 10 centimeter field of view. So you can see more details are there. Now it is 10 centimeter. Just think of TFOV as a physical thing. Okay. So now more details are available to you. Again, you want to convert from the left to the right. Okay. So you can see if you just focus inside the bone, you can see some artifacts. I'm not sure if you're able to focus. So there are artifacts inside the bone, while this is very smooth here. So this is a very, very good result, right? You get less artifacts here in the conversion process. Okay. Yeah, so this is some quantification. So whenever in CT, you always have some wire phantom data available. So you do quantification of your results. So this is how the wire phantom look like. Okay, earlier I had shown you water phantom. That is different. This is a wire phantom. Here we've quantified our results. So this is a direct learning versus a model-based architecture, and in comparison to input and target. You can see it is very close to the target. This is a good result. And if you quantify, if you estimate the MTF, which is the final task here, so then you can see that this is your input, right? And this is your target. You are reaching here. What you are doing here is you are minimizing some of the noise. Therefore, your proposed network is little bit less. But the direct learning, which is this orange curve, is like very low. If you do not have a mid-frequency boost here, then that is not a good thing. So you have a huge difference from the target. So that is not a good thing. Okay, so green one is slightly better. Okay, so and visually on the clinical data, it was significantly better. So, and why this is less? This is less because we are simultaneously doing artifact reduction also, which takes a toll on the quantification of the results. Okay, so yeah, so if anybody has any doubt, do let me know in the chat. Okay, so I'll just give a look to the chat if there is anything. Okay, I hope nothing is there. Yeah, okay. So we are all good. Okay, so this was about the supervised learning. So next we will just quickly go through the self-supervised learning, which is another kind of a unrolled architecture. Okay, so we'll just go through that one. Now we have some based on how we are unrolling. Okay, now only change that we are going to do is how we are going to do the same thing if we do the self-supervised manner. but this time using a deep image prior. Deep image prior is really a powerful concept. What do they say? If you have this kind of problem, y is equal to ax plus n, inverse problem to solve. If you're doing a simple supervised learning, you send your y as an input, okay, to the neural network, and you get a network prediction. You are minimizing between the ground truth and the prediction. So x is your ground truth, and this is your prediction. Okay, so this is what you are doing. Now in the self-supervised learning, what you do not have access to the ground truth. Then how do you calculate the error or the loss function? You calculate the loss with the help of your model, forward model. If forward model is available to you, then on the prediction. So whatever is your prediction, you apply the forward model to it. That will take you back to the input data, but it is this time y hat, and then you are minimizing the loss between y and y hat. And here in this case, neural network act as a regularizer. So this concept has been very much detailed, discussed in detail in this paper on deep image prior. Very nice reading if you want to get started on self-supervised learning. This is a very good way. Okay, so we are going to see how we can use it in our settings. Okay, so here we have experimented with something called a network regularized problem formulation, but a different kind of regularizer. So earlier what we were doing is x minus z. Okay, that was the in the MODL formulation, model based deep learning architecture. This is also model based deep learning, but here regularization is slightly different, and let us see how does it impact our results. Okay, so this is another way in which you can use a network as a regularizer. So right now, if you just assume R as a matrix, later on you change R to a network. Okay, if you derive the solution, then we know we can take a again. If this is a problem formulation, we can take a derivative, put it equal to 0, and get this as a problem, normal equation that we want to solve. Okay, and we know this is the solution. Only problem is we do not know how do we invert it. Okay, then what we can do? We can take the help of Newman series. What is the Newman series? We know what is a geometric series. Everybody knows. Okay, so geometric series for a scalar value. X is a scalar. Okay, in that case, we know this is the sum we can write. Exact same way you have a Newman series defined in mathematics, which is like this. Okay, just I'm giving you 1 minute to digest it. Okay, this is exactly the same. Just see the correlation between them. So if you want to invert, which is very much like this. Okay, so our goal is to invert this whole thing. And what we are exploring is a Newman series. This has been originally discussed here in this paper. Okay. Of course, there are some constraints here on the structure of A. Okay. But when you are really unrolling just like 5 iteration, 10 iteration, it doesn't matter. The constraint really comes into play when you have thousands of iterations. Okay. So what we were interested in, taking the inverse. Okay. So how do we take the inverse? So we know this is the problem that we have, and we know this is the Newman series. Okay, just assume some arithmetic we will do. I minus a is equal to eta times b. So you put this, then what is a? Just reshuffle. A is equal to I minus iota b from left to right. Now substitute this thing. So what you will get from here to here. Okay, so you get a b inverse is equal to this thing. Okay. Now you put b is equal to this thing, all this thing here. Okay, so you put b is equal to this, so you got this as a solution. Now, but can you simplify this? That is the task you have at hand. So yes, it is possible to simplify this solution. So you had this problem, you had this solution. Okay, so this is the solution that we had. Can we simplify? Yes, you can just assume that x naught is equal to A transpose Y. A transpose Y is always fixed. What is Y? Y is your input, and you apply the operator A transpose on it. So once you know A, you also know A transpose. This is very easy. Okay. So this is a constant term, x naught is the initial solution. Then you just expand this series. Okay. So you just expand this series by putting the different values of k. So k is equal to 0. K is equal to 1 is this term. K is equal to 2 is this term, and k is equal to 3 is this term. So, okay, so you expand the series, Then you define this recurrence relation. Okay, so this is the definition. So that helps you solve this problem more efficiently into the form of a neural network without making any assumptions here so far. So I mean, this is just some arithmetic operation which finally gives you a solution x hat, which is x naught plus x1 plus x2 and sum of this. What is xk here? The important thing is what is xk? Xk is defined like this. Okay, so now this is x naught that you had. This is xj that you define. Then you can represent this into the form of a neural network architecture. The important point here is this term, this yellow box does not have anything trainable, no trainable item here, nothing trainable, not trainable, okay? And this R, which was originally we were considering as a matrix, if you consider it as a neural network, any neural network architecture, which takes your input image, gives you an output image, CNN, RDN, anything, okay? That forms a recurrence relation, okay? Now you can expand this relation. Okay, so if you just expand it x0, x1, x2, what happens? The solution naturally has a form of, sigma xi. So this is very similar to your residual connections. Okay, but this is naturally coming out of the derivation of the Newman architecture. You didn't do anything specific to do it. So this is very similar to residual connection. And that is very helpful in training of a neural network. We know this, right? So this has a skip connections, okay? And so this helps you incorporate the physics very efficiently because this separates out these two blocks and this block is trainable. Again, you can have these shared weights or unshared weights. And then finally on Xn, what you do, you can do either DIP way or a supervised way. So you have a Newman architecture, which is this particular architecture, and then you can utilize self-supervised learning or a supervised learning, depending on whether you have a target available or not. Okay. So only thing pending is how do we handle the noise? I told you the noise in CT is very, very challenging. It is dependent on the kernel and kernel depends on resolution as well as your DFOV. Few things are there. Okay. So this is an example of the noise. Okay. So left one is your Gaussian noise and the right one is a water phantom actual data, which is used as a noise. Okay. You can see the texture. There is a lot of difference in the texture here. If you train your neural network using this one, it is not very much applicable here. Okay. So therefore it is important how do you handle the noise correctly into these trainings whenever you are handling. So that is the main thing. Okay. So what we do, we already have access to the water phantom data. So we add the water phantom data as an input. Then we get an initial solution using Tikhonov regularization. Then we utilize the architecture and finally get the network prediction. On the network prediction, I told you you can use a DIP as a loss function. So what this is the network prediction. Then you apply the forward model, which takes you to the input domain and you compare with the existing input. So that way you can minimize the loss. Okay, and then you apply it through the volume. Okay, so then you get, this is the result that you get. Okay, so this is the standard kernel image. Here you have the lung kernel image, which is like a target kernel. Now, when you apply this model, you can see you get a result in which noise is very much controlled. Okay, so you do see some of the edges have some artifacts here. You know, these lines here that can be taken care by doing some padding. Okay, so that don't worry about that. But look at this texture here in this region versus here. Okay, so the target here is not very good, but this is a preferred image. Why? Because the soft tissue texture has improved here. Okay, so you have reduced the noise while keeping a sharpness as a right side, but the texture like a left hand side. So left is a very smooth image. Okay, left one is a smooth image. So you kept the left kind of smoothness and right kind of sharpness in the main structures. So this is a very good result. So this is another like a coronal slice, sorry, sagittal slice, which is a different view. So you can see from, so this is again standard to the lung conversion, and this is the proposed method. Here you can see inside here. So much differences you can see. I gave you some time so that you can clearly see the difference between this one and this one. Okay. So there are a lot of fine details. So don't worry about the undershoot because this is a lung kernel data. You see some undershoots also here, right? So those undershoots are coming because we had the lung kernel, which was like, if I just draw it somewhere. Hmm. So like this, okay. So this was the lung kernel shape. Okay, and this was the standard kernel going like this. So whenever you have a kernel going more than one, you get an undershoot. So this is perfectly fine to see the lung. So therefore you see a lot of black data here. Okay. So here also you have, because this has been reconstructed using lung kernel, which is like going up to like 1.75. So don't worry about that one. But in general, you should be able to see like middle one has a more cleaner. So artifacts are less and the sharpness is equivalent of this one, the right hand side. Okay, so yeah, this is another result which is very interesting on the inner ear data. You can see from the left to the right. So left one is your input, right one is your ground truth, and the middle one is your output. You can see you go very close to the target. Here you can see all the details available. Here also you can see the structures compared to the left one, which is more blurry. Okay. Yeah, if anybody has any doubt to let me know. Otherwise, we conclude. So, two things to remember here. What we talked today about the one problem, which is called a kernel's conversion problem. Okay. So everybody should be able to understand like what is the in general kernel conversion. When somebody has a like one input kernel, you want to go to a target kernel, but in the image domain. So this problem is relatively easy. So what you are doing, you have one kernel, you went to another kernel, but you didn't change the bandwidth here in the frequency. So this is the frequency here in the x-axis. You didn't change the frequency. You have a more difficult problems in the super resolution. For example, if you have one kernel here, another kernel dying here, then you want to increase the bandwidth. That becomes a bandwidth enhancement problem or the super resolution problem in medical imaging. So I hope somebody might be covering. So this is the problem that comes more often in both CT/MR at least. So you want to enhance. So that is also a kernel conversion. But that kernel conversion is what we didn't cover today. Okay, we only covered when you want to keep the bandwidth same, but more focus was on the noise and the artifact management using a architecture that was a model-based deep learning. So I hope what is clear to everyone is what is model-based. Model-based means you are imposing physics constraint explicitly. Whatever information you have, this is very much true in your MR also. For example, you have a lot of coil sensitivities or you have a lot of like subsampling mask. When you are scanning, you also have, in diffusion, you have the different phase errors and also a lot of information is a priori available about the scanning procedure. So all those information can be modeled into your A operator and that helps you learn effectively than a direct learning method. So that all information which goes into the A operator is why about the model. Model essentially refers to your scanning procedure or the way you are you are posing the problem statement. What does it mean by input and target relation via the A operator? So that is the model constraint. And when you use DL as a regularizer, which is a very good regularizer because it has a lot of good things like you learn a very good regularizer from the existing data and you have a lot of data. So you want to utilize that also. So you utilize the best of both the classical algorithms as well as the latest algorithm and you combine them into medical imaging because you don't want to make a mistake into the reconstruction. Suppose you did some reconstruction, but if you hallucinate with the help of model based deep learning, you reduce the chances of your hallucination because you always put a constraint on y is equal to ax kind of constraint, right? This kind of constraint always help you with the reduction in your chances of hallucination because you always ensure whatever is your original data, which is y is your original data. You don't go very far from y. You make some changes into your x, but don't go very far away from y. That is the primary goal here. Okay, so I hope these two things are clear to you. What was the architecture and what was the kernel conversion? So with that, yeah, if you guys have any questions, yeah, do let me know. You can connect with me here on this my email ID. Yeah, that's all I have. I'm open to any questions you guys have. Okay, please feel free to ask. Thank you.
Yeah, thank you very much, Dr. Hemant, for your wonderful talk. And I think participants have got some idea about how to use the traditional approach, how to incorporate convolutional neural network, as well as you have talked about self-supervised learning paradigm. So they might have got a lot of ideas. I mean, how the real-time problems can be solved by combining both. I mean, the traditional one as well as the deep learning. And also, you have explained beautifully the mathematical. I mean, starting how it got started and then how the problem got complex, little bit complex by adding so many regularization term and so participants. Yeah, I mean, also we have got some comments from participants. It's a very informative session. Yeah, if you are having any query, participants, please write in the chat box. Dr. Hemant will happy to take your question. Any other queries?
Yeah, you guys already have my email ID. So if you have a question later on, you can directly ask also.
Yeah, we'll wait for only 1 minute. Let's see.
Yeah.
They may take some time to write. Okay. Mm. Yeah, I don't see any
Yeah.
queries from the participants.
Yeah.
So,
So
participants,
yeah,
if you want to, I mean, discuss anything or if you're having any queries, you can also directly email or directly drop a message. You can say you can drop an email to Dr. Hemant and he'll be happy to reply you back
sure.
with some
Yeah.
answer.
So and yeah, thank you very much everyone, and thank you Deepak for the opportunity. Yeah, very
Yeah,
nice session. Yeah, thank you. Happy to present. Yeah, thank you
yeah.
everyone. I'll take the
Thank you
leave
so
now.
much. Yeah, thank you.
Yeah, thank you. Bye.
Yeah, participants, so I would request all of you to please at least try to interact with the speakers. We all know that they are expert in this field, right? They're working in various domains, they're working in industries and all. So, but if you are not able to understand, you can just write your, I mean, query in the chat box. They will be happy to answer. Okay, so we'll be having our next session after 5 minutes, and our next session will be delivered by the Professor Vinayak Ringa, who is a clinician, renowned clinician across, I mean, India. So he's currently working in SMS College Jaipur. Okay, I will also talk about him more right when he joins with us. Okay, we'll start after 5 minutes.